So, but as I said, today we're scheduled to finish up with the material in chapter 16. We've already covered nucleophilic aromatic substitution, but I thought it wouldn't do any harm to go over it again. So I just wanted to do one other example. Basically, you want to look for a nucleophilic aromatic substitution type scheme when you've got an aromatic compound with a good leaving group. Someone asked last time, can you use tosylate instead of halogen? Again, I've never done one of these reactions, but I certainly believe so. I don't see why you couldn't. But you want to, at least you want a good leaving group, and preferably at least one electron withdrawing group. So nitro isn't the only electron withdrawing group. There are many others besides. This compound would be very well set up for a nucleophilic aromatic substitution. In fact, whenever I see sort of 1,3,5 trinitro on a benzene ring, I get a little worried. You might have heard of TNT, which is 2,4,6 trinitrotoluene. So you can figure out the structure of that. It's basically, instead of the tosylate, you'd have CH3. So anything like that tends to be un poco explosive. But since we're just doing this on paper, no one will get hurt. But in the first step, I would expect whatever nucleophile you're given, in this case, we're using sodium hydroxide and water. We've done some other examples of ones with good nucleophiles. But that's going to attack wherever your leaving group is. It's going to attack the same carbon that's bearing the leaving group. The intermediate you get is a carbanion. And honestly, you can put that, that negative charge on any of 3 different carbon atoms. Remember, when you're writing a mechanism that goes through a resonance stabilized intermediate, well, you can use whichever resonance form you want to. There will be a correct way to write the mechanism. I believe someone asked me the other day, do you have to show all the resonance forms? Not if it doesn't say to, right? I think you know the drill by now. You have to do everything it says. You don't have to do anything it doesn't say. So normally we don't do that. Anyway, you do get this resonance stabilized carbanion. There's also minus charge on this carbon and minus charge on that carbon. And look at that, the minus charge is shared amongst all 3 carbons that have an electron withdrawing group directly attached. So no wonder this type of reaction is so favorable when you have a setup like this. And so once you have after you have the carbanionic intermediate, that's going to fall apart and regenerate the aromaticity. We'll reform that pi bond. We'll kick out our leaving group, and you get your product. So that's a typical nucleophilic aromatic substitution process. Goes through 2 steps. And again, this is neither SN2 nor SN1. This is something entirely different from both. Whereas SN2, you'll recall, is all 1 step. So an SN2 reaction with the hydroxide comes in, kicks out the tosylate, and you're done. That does not happen. That's been experimentally determined not to be the case. The SN1 process goes through 2 steps, the first of which is loss of the leaving group to get a carbocation, and the second of which is deprotonation next to the carbocation in order to generate a new pi bond. And that's not what's happening here either. This goes through a carbanion intermediate. And so in advanced organic books, like if we were doing a 3rd semester organic type class for juniors and seniors, we'll learn that there are names for these others. It's been a long time since I've taught a course like that. But I believe that type of reaction is called an SNAR, AR for aromatic. So, but in any case, that's not important for us. Main thing is to understand that this is neither SN2 nor SN1. So I figured it wouldn't do any harm to do one more example of a nucleophilic aromatic substitution. But the mechanism in general, we expect to have 2 steps. First, attack of the nucleophile to generate a carbanion, resonance stabilized carbanion, and then that species falls apart, kicks out the leaving group, and we get our aromatic ring back. Good, make sense? Any questions on this example? You mean I did it again? And on a Friday even? Wow. I better put that in my annual report. Okay, So there is another type of reaction that really, to me, falls in more or less the same category, at least sort of the same zip code as nucleophilic aromatic substitution. It's really a kind of nucleophilic aromatic substitution because in both cases, both the case of benzyne and the case of a standard nucleophilic aromatic substitution like this, as someone pointed out in the previous class to you, probably a lot of you are thinking the same, really here our aromatic ring is the electrophile. It's reacting with a nucleophile and it's accepting electron density from that nucleophile, from that Lewis base. And so our aromatic ring is very much the electrophile in this reaction. Of course, in an electrophilic aromatic substitution, now your benzene ring is the nucleophile because you're treating it with a strong electrophile, and the benzene ring now has to put out an electron pair to react with that electrophile. So I don't know if this makes sense. I like to think of it when it says electrophilic versus nucleophilic aromatic substitution, they're not talking about the benzene ring, they're talking about whatever you're treating the benzene with, right? So here we're treating it with a nucleophile, so it's a nucleophilic aromatic substitution. The other ones we did earlier on, a few lectures ago, those are electrophilic aromatic substitutions because we're treating the aromatic compound with an electrophile. The aromatic compound itself acts as a nucleophile. So that's the way I like to remember it. It's a little confusing at first, but I think you guys will get it. Benzyne really, to me, is another kind of nucleophilic aromatic substitution, but it's the kind you get when there's no electron withdrawing groups on the benzene ring. Up till now, we've always had some big fat nitros or fluorines or something like that on the benzene ring. Here we don't. So the question then is, can it still undergo a kind of nucleophilic aromatic substitution? Answer is yes, but it goes through a different pathway. It goes actually through an E1CB reaction. So you might want to review that in chapter 11, along with, if you need to refresh your memory on what Sn1 and Sn2 reactions are like. But all of that is in chapter 11. So we covered all that earlier. But when you have an aromatic compound that has a leaving group, doesn't have to be chloride, doesn't even have to be a halogen. Again, I think tosylate or any alkyl sulfonate would work just fine. But you don't have any electron withdrawing groups attached. Then there is still another possibility, and it goes through, believe it or not, a benzyne intermediate. And I always have to tell a story. Years and years ago at my previous school, this was probably between 10 and 15 years ago, somehow, by some strange coincidence, the day that I lectured on benzyne was April 1st. It was April Fool's Day. And so everyone was going, oh, come on, Dr. Wass, this can't really be a thing. Benzyne, come on, April Fool, right? And I think they kept doing that for several minutes afterwards, even though they believed me, just to kind of irritate me a little bit, which I get. But it's not April Fool's. Benzyne is a thing. And we get it by an E1CB reaction. And if we recall, the way an E1CB mechanism works is we first deprotonate on the carbon next door to the one that bears the leaving group in order to generate a carbanion. That, relatively speaking, is going to be the fast step. Right? Recall that anytime you have a proton transfer, those are always very fast. The slow step in comparison is going to be the next one, when this carbanion collapses, forms another pi bond, and in doing so kicks out the leaving group. So you do form this benzyne intermediate. Strange but true. This has all been experimentally determined. They've detected the carbanion intermediate and they've detected the benzyne intermediate. So as you can imagine, benzyne is an exceedingly strained compound, right? Your sp hybridized carbons want to be linear. We're nowhere near linear. Of course, before this, we were at 120 degrees. I don't know the exact, I don't remember the exact structure of benzyne. I just don't have that off the top of my head. I wouldn't be surprised if it, distorted I'm sure it's not a perfect hexagon any longer. And I wouldn't be surprised if those bond angles are like 140 maybe, but we're still nowhere near 180. So the driving force for a nucleophile to attack one of those two carbons is very, very high, very strong. And in so doing, once we break that pi bond, we generate this type of carbanion, which, although an aromatic carbanion, which isn't so great, still a heck of a lot better than benzyne. And this, by the way, is how phenol is made by the ton every day in America and elsewhere. Phenol is made from chlorobenzene by treating it first with aqueous sodium hydroxide. And they add some other things besides that. I believe they add some sodium carbonate in order to buffer the solution somewhat. This, by the way, is no walk in the park. You need really extreme conditions in order to do this. High temperature, high pressure. This is not the sort of thing you can just do in a little flask right there on your lab bench. This requires pretty extreme conditions and pretty extreme equipment. But once we get through to this point, of course, our carbanion will very quickly pick up a proton from water, since that's pretty much all we have available. And for a moment, in this particular case, we've generated actually our product. And so we're done, right? Well, no. No, because we've generated phenol in the presence of aqueous hydroxide, in the presence of a very strong alkali. And so phenol is going to have a pKa round in about 10, somewhere in there. We're here maybe at pH 14. So this is going to get deprotonated, and you can't stop that from happening. And this is not the first time we've seen this type of reaction, nor will it be the last time we see this type of reaction, where we generate an acidic species in an alkaline solution. And in that case, the acid is going to get deprotonated. Sometimes later on, for instance, when we learn about alkaline hydrolysis of esters, we'll run into a situation where we generate a carboxylic acid in the presence of an alkaline solution. And so that carboxylic acid is going to get deprotonated. You can't stop it. So actually what's going to be floating around in our mixture is the phenolate ion. That will be swimming around quite happily until we acidify. So this reaction does require a second step, an acid workup. And when we add the acid, the first thing the acid is going to do is kill off any remaining sodium hydroxide. So neutralize all the base. And after that, it will start putting the proton back onto the phenolate ion so that we can isolate our free phenol, right? We don't want to be isolating ions. We want to isolate a neutral molecule. So I've written down here just a reminder of the principle behind all this. Whenever you're writing a mechanism, it shouldn't ever be something you do mindlessly and blindly, just sort of regurgitating. You need to be thinking at each step of the way, why am I drawing this structure? Hopefully these are questions you've asked and answered during your studying process. Why am I drawing this structure? What was the driving force to get here? What's the driving force for what happens next? Is the structure I'm drawing, or does the structure I'm drawing make sense given what's in the reaction mixture? Or is there going to be some further transformation? And again, we've got aqueous base here. You have to look always at what you're given. We've got aqueous base and our aromatic compound, and that's it. And that aqueous base is still going to be here all the way through, including when we get our phenol over here. So as I said, we're not going to be able to stop this from occurring. We need to show this happening, because it's going to happen. The hydroxide is more than strong enough as a base to pull off the proton from phenol. You can't add the acid fast enough to prevent this from happening so that you don't have to show it. If you tried doing that, you'd wind up with an incomplete reaction. There'd be leftover chlorobenzene. So instead, we add the base and we wait. We let it all react until nothing more can happen. And that's the point. That's the point where we have phenol, the phenolate ion rather. Then we add acid. and that will neutralize any leftover base plus reprotonate the phenolate ion, and then we can isolate the free phenol. And phenol is no unimportant, because the second step with the H3O plus gets rid of the aqueous base. Yup, that's what will happen first, actually. It will just react with any leftover base, according to the familiar equation, OH minus plus H3O plus yields 2H2O. And then, once the base is all gone, then we start putting the proton back on the phenolate ion. But of course, we will add enough acid to do that. There's not really any point doing it otherwise. But that will then put the proton back on and will isolate the free phenol. So yes, that's correct. It does both. Generally, workup steps have two, they often have two different things that they do. One is what you just referred to. It will destroy anything left over that's reactive, so that you can isolate your compound safely. And the other thing the workup step will often do is protonate any anionic intermediates, so that you get a neutral compound to isolate. So I would say it does both in this case. Check back when we talked about lithium aluminum hydride, by the way. That had an aqueous workup step. You would add either H2O or dilute aqueous acid, doesn't matter which. The first thing that's going to do is react with any leftover lithium aluminum hydride. And believe me, that reaction is exceedingly violent. But so you want to do that before you try to isolate your compound, so you can do so safely. And then you do also get an alkoxide intermediate in that case, and that will then also put the proton on that oxygen, much like over here. So I just wrote something over here as we were talking about this with my previous section, just to give you something to review on that matter. But this is not going to be a rare thing for us. That you need to think carefully about the structure of what you're drawing. And that's why we don't just stop here, even though that's our product. We need to be aware we've generated that molecule in aqueous base, and it's going to get deprotonated. And so it will all go towards the phenolate ion. And then later on, after everything's done reacting, then we add dilute aqueous acid. So one other thing I should say, I was beginning to say actually, phenol is no unimportant compound, by the way. This is something that that we need on the multiples of tons basis every day. Phenol is the starting material for, well, first of all, phenol is an antiseptic in its own right. I don't know if you use or you know anyone who uses, my dad used to use this stuff. Like that Listerine mouthwash that's kind of yellowish orange maybe and tastes kind of medicine-y. The medicine-y taste is phenol. It has a few % of phenol in it. So it's an antiseptic. Also, phenol is the starting material for things like salicylic acid and aspirin, though we get some of that naturally also from willow bark. But and once you have those compounds in turn, you've got precursors to various artificial sweeteners. So phenol is a very important compound industrially. And there's also other things that we can do with benzyne also. But to me, really, benzyne is sort of a special type of nucleophilic aromatic substitution, because we're still treating the aromatic compound with a nucleophile. Doesn't have to be hydroxide. There's various others that would also do the job for us. So please review in chapter 11 so you're familiar with what makes something a good nucleophile, what makes something a good leaving group, etc. That would not be a waste of time to review those things in chapter 11. But I mean, bizarre mechanism, well, except we've seen it before, it's an E1CV mechanism, but bizarre intermediate. But like I said, don't shoot the messenger. Benzyne has been experimentally determined to be an intermediate in this reaction. Good, can't really think of anything else to say. Any questions or comments on, any questions or not rude comments on benzyne? Nothing that we would need to censor. Nothing that couldn't go on Twitch. Well, no, people do swear on Twitch, don't they? Do we need to know the full mechanism? Well, If we cover it in class and if it's in the book, then you need to know it. This is only one particular example, but in this particular example, we wind up with an acidic species. So you need to be on the lookout when that's going to happen. Sometimes it will happen, sometimes it will not. So, but in general, the answer to the question, if you need to know something, if we go over it in class, then you need to know it. If it's in the book, you need to know it. Unless I specifically say you're not responsible for it. Good. Other questions then? Well, look how, oh, can you go over the benzyne with, well, yeah, now that no, I'm not going to do it after class. I'm going to do it next. You're one step ahead of me. Because that's the other thing. Well, actually, I'm not going to go over the mechanism. I am going to set it up for you, because I think you guys will get a lot more out of it by working it out on your own. I am going to show you what the product looks like. So that's another thing you can do with benzyne. Benzyne makes a really, really great Diels-Alder dienophile, as you can imagine. I mean, you've got an we already know that alkynes can act as Diels-Alder dienophiles. Here you have not just an alkyne, but a really, really strained one. One that after it reacts, you wind up getting the aromatic ring back again. Let me actually draw this the way I had it originally. That might make it a little easier to comprehend. So as an example, let's say we started with bromobenzene. I could have used chlorobenzene or phenyltosylate or any such thing. And then you treated with some strong base. I could have used sodium hydroxide and water. Sodium amide and liquid ammonia will also work just fine. So see if you can work out that mechanism. It's just like what we did before with the chloride and with hydroxide, except we've got a bromide, and instead of OH minus, we have NH2 minus. Same exact mechanism, 2 steps to give us the benzyne. And the only twist is that we'll have some Diels-Alder diene also in there at the same time. We would need to have that in there, because I'd be worried this would decompose and do weird, unspeakable things if we don't have something there already for it to react with. And so actually, I think that that the cyclopentadiene will be more reactive toward it even than NH2 minus. And I bet you would get a pretty good yield of this bicyclic aromatic compound. And I've shown you here those 2 red bonds are the two new sigma bonds. How do directing effects affect benzene reactions? Good question. Remember, directing effects only apply to electrophilic aromatic substitutions, not to nucleophilic aromatic substitutions. The way you know that is because in a nucleophilic aromatic substitution, the nucleophiles always go to attack where the leaving group is. So there's no ortho-meta para-directing stuff with nucleophilic aromatic substitutions. There you know where your nucleophile is going to add. It should be wherever the leaving group is. So that's how you know that. Same thing with benzyne. There's no directing effects per se. Orthometa and para-directing effects will apply only to electrophilic aromatic substitutions, because those are the ones where the issue comes up. Where do you put the new group? With these types of reactions, it's clear, so there's no directing effects. I'm glad you asked that, though. That's a good question. Anyway, back to our friend over here. So I would anticipate that you would get this compound in pretty darn good yield. Where does the triple bond go in the Diels-Alder reaction? Well, it's the dienophile. So you just put that triple bond wherever you would have put your dienophile. That could have been, and we gave various examples of dienophiles. We did one with an alkyne. So just put that triple bond where the triple bond of the alkyne dienophile goes. And the mechanism is exactly the same. And you'll find in so doing, you just get a benzene ring back. It'll be fused with this, just going to make sure. Yes, yep, that's correct. And these 5 carbons come from the cyclopentadiene, these 6 from the benzyne. And so these 2 bonds that are red are the 2 new sigma bonds. Your new pi bond is over here. Maybe I should make that red too. Doesn't cost me anything. So that's where your new pi bond is. So that would be worthwhile. That would not be a waste of time for you to work out that whole mechanism and convince yourself that that's the product that you get. Good, so I'm going to leave the mechanism for you guys to work out, since I think that will be good practice for you, especially since the Diels-Alder reaction is in this exam's material anyway. But I thought I would at least give you the structure to aim for. I believe that's the product you'll get. Good. Other questions about benzyne? Could you go over or post the solution later? I really don't want to do that. I want people to work it out on their own, but what I will say, if you want to come to office hours and show me what you've done, and I'll be happy to look at it and see if you did it right. I think you'll know, though. I bet you'll have confidence once you actually go ahead and do that. I've done the hard part. I've shown you the structure of the product. But yeah, that offer is always open. Or if you work out any other problems, maybe you've made up some problems and you want to see if you've got the right answer and done it right, you want to bring them to office hours, please don't hesitate. That's what I'm here for. I even, thank goodness, have some in-person office hours. I was worried I wouldn't get to have any. Good, so much for benzyne. Strange but true. The only other thing I really wanted to go over today was some particular redox reactions of aromatic compounds. And this will go relatively quickly, since none of these will involve your learning a mechanism. These are all probably going to go through single electron transfers. I'm sorry, I'm still thinking about putting up the solution. I'll think about it if I get a chance. I'd rather you guys worked on it. I just don't want people to go there and copy it and think they know it. You'll get much more out of it if you go through it, really. But sure, I'll be happy to go over that with anyone. Good, so as I was saying, these are oxidation and reduction reactions that involve aromatic compounds. And so we're not learning any mechanisms here. I don't think the mechanisms are even really known. But they're all going to involve either oxidations or reductions. One really common one involves alkyl benzene. So here your R can be any alkyl group, any chain of any length with other chains branching off wherever you want, however long or short you want them to be. This is a reaction with aqueous potassium permanganate. And you may recall that the permanganate ion is one of the strongest oxidizing agents known to man. I mean, it's right up there with periodic acid, and these things are just potassium dichromate. These things are just stupidly strong oxidizing agents. And in the end, what you wind up getting is benzoic acid, or a benzoic acid derivative. The carbon in the alkyl group, that's the one that's directly attached to the benzene ring, becomes the carboxylic acid carbon. Any and all other carbons get chewed up and oxidized all the way up to CO2. So that's the only organic product. But any other carbons in the aromatic ring just get chewed up and spat out as carbon dioxide. So again, the carbon that winds up in the carboxylic acid carbonyl used to be the one carbon that's attached directly to the benzene ring. That's the one that becomes the carboxylic acid carbonyl. All of the any and all other carbons in the alkyl group get oxidized all the way to CO2. And again, let's not fail to notice the rest of the benzene ring doesn't get touched. That's pretty amazing. There are very few things that will not react with potassium permanganate. Benzene is one of them. So that gives you an idea of just how stable this ring system is. This is a strong enough oxidizing agent to convert alkyl carbons to CO2, and yet it doesn't touch the benzene. I think that's just astonishing. And I think that's the sort of thing that, that one does well to notice, because it helps cement in our heads, wow, this is a really stable compound. There's just not a whole lot that you can do with it in terms of redox. Another thing, this is actually a blast from the past. We talked about this back in chapter 10, where we discussed N-bromosuccinimide, NBS. That's a reagent that will replace benzylic and vinylic hydrogens with bromines. So please review the structure of N-bromosuccinimide. I don't want that just to be 3 letters to you, but this is a radical reaction. So you need either light of a particular wavelength you need heat, or you need a radical initiator to get this thing started. But remember also this really unfortunate term, benzylic. It's such a shame that they decided to use that name, because our tendency, if we hear something like benzylic carbon, it sounds like it ought to be one of the carbons in the benzene ring, but it's not. Benzylic refers to the position next door to the aromatic ring. Excess would bromate all benzylic H's correct. And not only all benzylic, but if there's any allylic, yep, excess will get all of them. I don't know a good way of getting just some of them selectively. I think you'd get a mixture. So I think best practice would be to use one equivalent and just replace one of them, or excess and get all of them. But certainly you need one equivalent at least for each hydrogen. But again, just a reminder, benzylic means that you're next door to an aromatic ring. So we call that type of carbon benzylic, and any hydrogen attached to such a carbon we would call a benzylic hydrogen. It's a very unfortunate name, but it was decided on over a century ago. None of us was around to complain at the time, including me. Even I'm not that old, and you know, we're stuck with it. So just refresh your memory on that. But the reaction usually is done in some halocarbon or hydrohalocarbon solvent. Carbon tetrachloride and chloroform are both pretty common, CHCl3. And again, the end result is that you will replace a benzylic hydrogen with a bromine. And of course, you get HBr as an inorganic side product. And just like someone asked, if you have multiple benzylic hydrogens and an excess of NBS, you'll get all of them. So, but we talked, that's not a new reaction. We talked about that one back in chapter 10. So please do go back and review that. That also, by the way, counts as an oxidation reaction, because we're replacing a bond to hydrogen with a bond to an electronegative element. So anytime we replace bonds to hydrogen with bonds to halogens, oxygen, nitrogen, things like that, that's going to be, that will technically be an oxidation. So these ideas are all in your textbook, of course, but it's one way that you can know that whether you're looking at a reduction or an oxidation. The opposite, by the way, would be a reduction. If we converted this bromide to that hydrocarbon, which there's ways of doing that, that would then be a reduction reaction, because we're changing a bond between carbon and an electronegative element to a bond between carbon and hydrogen. So the reverse process would be a reduction. And something also to be aware of, it's very possible for a reaction to be neither oxidation nor reduction. So you'll get plenty of practice with that on OWL. It's something that I think is useful, because anything you can do to categorize reactions will help you to learn them. Anything you can do to put them in boxes will just make things more organized for you. That's my belief anyway. So then the question comes, can you reduce aromatic rings? The answer is yes. In other words, can you hydrogenate them? You can, but it's much more difficult than with alkenes. Mere palladium or nickel or something like that would not be good enough. Rhodium is usually the transition metal catalyst of choice. We had to look that up on the periodic table with my last class, or by which I mean to say I had to look it up. I knew it was in the D block. And so you will find it indeed in the D block right under cobalt. As I recall, it's element number 45. So rhodium metal is much more reactive as a catalyst than palladium, nickel, ones like that. And this also, in general, requires a pretty goodly excess of hydrogen. Of course, you need at least 3 equivalents anyway. Should really have written 3H2 at the very least. It's not too late. We can still do that. So you need at least 3 equivalents of hydrogen, right? But you probably have a lot more than that. And in general, it requires extremes of both pressure and temperature as well. So it is not easy to do this reduction. It's possible, but you got to really kick it. And in the end, one would expect to get a cyclohexane derivative. And since, as we said in chapter 8, when we discussed hydrogenation, addition of H2 is in a syn fashion, SYN, meaning the hydrogens get added cis to one another, I would expect any and all substituents on the ring to turn out to be cis in the product. So at least I would expect that this would be the structure of the product that you get. So that's a reduction reaction because we're adding more bonds to hydrogen. And so anytime you're doing that, anytime, or another way to think about it is we're reducing bond orders. We're going from carbon-carbon double bonds to carbon-carbon single bonds. That also falls into the reduction category. And there's more than one correct way to come to that conclusion. But this would be then an example of a reduction reaction. Good, I think that's pretty much it for redox of aromatic and benzylic carbons per se. Everyone okay so far? We're nearly done. Let's see. Right, couple more reduction reactions that I think may come in handy for, I don't know why I put LAH there. Anyway, that may especially come in handy for you guys when you're looking at synthesis problems involving aromatic compounds. One thing that you might find yourself needing to do is to reduce an aromatic nitro compound to an aniline derivative, an aromatic amine. And there's actually a few different ways to do that. One uses iron metal. So again, please notice that's iron 0, right? Elemental iron, iron metal. I think it would come as a fine dust. That would be my guess as to what you would use. You also need aqueous acid, and then that will require an alkaline workup, because actually this is a similar idea to what we had before with the phenol, and we kind of turned on its head. Of course, aniline is a basic compound, it's alkaline. And so in an acidic solution, that's going to turn out to be NH3+ over here. And we don't want that, we want a neutral compound. So we do an alkaline workup that will remove that proton and allow us to isolate the free aniline. So that's only one way. There's another set of reagents, I believe, that involves tin 2 chloride. Catalytic hydrogenation will also do this for you. So there's a few different ways to do it. I don't care which way you learn. But that's one that you might wind up wanting to do, because I don't know of a good way of putting an amino group straight on the ring, at least in an electrophilic aromatic substitution. But nitration is pretty easy to do. And so that's a step that you might find yourself in need of having to do. And then another thing that might come in handy, we already know that you can get ketones of this type using a Friedel-Crafts acylation. And sometimes you'll find you want to reduce that ketone carbonyl all the way down to a CH2. And there's multiple ways to do that as well. There's a method that involves cooking it at very high temperatures in, I think, ethylene glycol solvent in the presence of, what do you call that stuff? H2N and H2, hydrazine. That will do a disproportionation reaction, and you'll wind up getting the fully reduced compound with the CH2. There's other ways as well. There's a reduction with zinc metal. Zinc metal is a very good reducing agent, or you can just do catalytic hydrogenation with palladium. That will also work. And I would expect in any of those cases, the oxygen in the carbonyl to wind up in a molecule of water. And the reason that this is so powerful is that compounds of this type in general, you will not be able to get by a Friedel-Crafts alkylation, right? Because this alkyl group will rearrange to a more stable carbocation before it even goes onto the benzene ring. So by using an acylation instead, that's the only product possible. With an acylation, you're not going to get any carbocation rearrangements because that acylium ion is resonance stabilized. So that's the only possibility. And so then, with careful planning, you can get a compound of this type selectively without having to worry about carbocation rearrangements. So that type of reduction, and again, I don't care if you use one of the other sets of reagents, that's fine. There's 2 or 3 ways of doing that, just like there's 2 or 3 ways of doing this. any and all of which are perfectly good. Any of those is fine, but you can reduce an aromatic ketone to the CH2. And the reason all of this matters is when you get into synthesis problems involving aromatic compounds, which certainly will be fair game for the exam, and certainly you will find in the OWL assignments as well. And the main bit of advice I have, since we have 5 minutes left, I'm actually somewhat minded. I don't want to be Amine. I'm somewhat minded to go back and get more into detail about that Diels-Alder reaction. So I would like to use the last couple minutes just for that. But be that as it may, in terms of synthesis problems involving aromatic compounds, the one bit of advice I can give you going into that as you start practicing is bear in mind that the order that you do the steps matters a lot. And that all depends on what product you're trying to make. For instance, let's say that we're making a product like this versus making a product like that, or maybe we want to make first one and then the other. Well, how are we going to go about doing that? Well, we know how to put a bromine in an aromatic ring. That's elemental bromine with aluminum bromide or iron 3 bromide. Likewise, we know how to put a nitro group on. That's going to be nitric acid and sulfuric acid. But which do you do first? And the answer is it depends which one of these you want to make. In this case, if you start with the halogenation, if you first treat benzene with bromine and aluminum bromide or iron 3 bromide, that halogen you put on is now an ortho-para-directing group. And so if as your second step you do your nitration with nitric acid and sulfuric acid, well, I would expect you'd get some of the ortho compound as well as the para. I would also fully expect the ortho compound to be the major product. It might, in fact, in real life not be, but I think it would be reasonable to expect that. So that would be the way you would get the para compound. But what if you wanted to make this compound? Then you would want to nitrate first, right? Because you'd first treat benzene with nitric acid and sulfuric acid to give nitrobenzene. And then you would treat the nitrobenzene with bromine and either aluminum bromide or iron 3 bromide, because nitro is now a meta-directing group. And so that will make sure that the bromine goes on in the meta position. So the order that you do these things in matters a lot. And you'll see that when you practice those problems in OWL. Good, so that leaves me 3 minutes. Before what I think I'll do is, I think you can get from here to the benzyne on your own. I'm not going to give that to you. We did that in the other page anyway. Right at the bottom of this page, we did this with chlorobenzene and hydroxide. So all you need to do is change the chlorine to a bromine and hydroxide to NH2 minus. The mechanism is the same. I think you can work that out on your own. So what would that Diels-Alder look like? Well, you might want to, actually, I know what I'll do. The cyclopentadiene is going to be your diene, right? And then the benzyne is going to be your dienophile. So they'll line up like that. There's no law that says the diene is to go on the right and the dienophile, the diene is to go on the left, and the dienophile on the right. If you like to put in the dotted lines, if you find that helpful, that's going to be where we form our, wait a minute. One other thing I forgot that's kind of critical. Yeah, it's benzyne. So that's how it's going to line up. And bonk, 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 just like always. Wait a minute. Not quite sure which type of arrow I have. I don't like that kind. Let's do this. That one there. That one there, just to make it easier for you to see. This one goes over there. And that leads to the product directly. Let me, as a last thing, number these carbons just so you can see. I just want to make this as visual as I possibly can. I understand that a lot of students are visual learners, and so the numbers that you use don't really matter. Also remember, I went clockwise with my arrows. If you went counterclockwise, that's fine too. It isn't really either one or the other. Rather, just everything goes whoosh all at the same time. So let me see now. This is actually going to be 1, since we flipped it over. 1, 2, 3, 4, 5, 6. And so this CH2 up here is the CH2 over here that's in cyclopentadiene. That just goes along for the ride. That's not involved in the reaction. So there you go. Hopefully that helps somewhat. But I guarantee you that reaction would go like a shot. The key to it is adding your base/nucleophile and the diene. You would want to have that present from the beginning, so that as soon as you generate any benzyne, it will react with that. And my expectation is that reaction would be even more spontaneous than the reaction with NH2-. And I would bet you would mostly get this. Good. Of course, I suppose it would also be kind of smart not to use a huge excess of NaNH2. I wouldn't go using 10 equivalents. Then I would worry that you'd start getting some aniline also. But, I mean, I've never done a reaction just like that, but sort of best practice suggests that to me. Good. Any other questions then? Well, in that case, I am out of time. So have a great weekend, and I'll see you all on Monday.